Forces and torques in the body. So when you're operating a nutcracker, so we have a nutcracker sitting here. It's a cute squirrel shape. Consider the rivet holding the nutcracker at the pivot right here, right there. So pushing on the handle causes force on the nut, which in turn causes force on the handle. So we push down right here, and then we have the handle pivoting right here, and that causes the nutcracker right here to operate on the nut, which in turn pushes back on the handle. So there's a positive torque at the hand and a negative torque at the nut. Because of static equilibrium, the magnitude of these torques must be the same. So if you picture that, because of this long radius here, we're creating a massive, well, maybe not massive, but we're creating a very large torque compared to this little radius right here, right? Now, if we have a balance of torques, this very large torque with a smaller, relatively smaller force that we're applying with this shorter radius right here, what must be true about that force right there?
It's equivalent. Right? No, it's
The torques are the same. So if this radius here is much larger than this radius here and the torques are the same, what must be true about the force that's being applied on the nut?
Yeah, it's greater than the hand.
That's right. The force that's being applied to the nut must be much greater than the force that we're applying at the hand.
It's a torque converter.
It's a torque converter. That's a good way to put it. So therefore, the force on the nut must be greater than the force on the handle. And so this is known as leverage or mechanical advantage. So this is a phrase I've used maybe a couple times here and there if you've ever picked up on it. We're creating mechanical advantage on a nutcracker. We would create mechanical advantage with levers, and that's basically what we're dealing with here is a lever. It's a simple machine. So examples would be cannon bottle openers, pliers, any pry bar, a shovel. We use the mechanical advantage of levers and pivots all the time. We create massive amounts of force on one end compared to the other to generate that equal torque, but larger force on the other end. So assume that your foot pivots as a single structure about a single pivot in the ankle. So if we take a look at this picture, we have a nice looking picture of a foot here with the ankle pivot sitting right here. Okay, so that's what we're talking about is the ankle pivot. Now the foot is obviously, we're up kind of on the ball of our feet, on our toes. So we have a force generated here. We have our pivot happening right here. And then the Achilles tendon is what's helping us lift up off the ground. Okay, you can all picture that. You've all gotten up on your toes before. Now we can move over to the much simpler model. Obviously, much simpler model, right? We have a pivot right here. That would be our ankle. We have the force of the floor sitting right here. That would be our toes. And then we have over here this force. That would be the lifting up off of the floor of our heel from the Achilles tendon. Okay, so when you stand up on your tiptoe, your foot pivots about your ankle. There's an upward force from the floor, a downward force on the ankle from the lower leg, upward force on the heel from your Achilles tendon. Suppose a 61 kilogram woman stands on one foot on tiptoe with the sole of her foot making a 25-degree angle with the floor and the distances that we see here. So what is the magnitude of the tension force in the tendon, and by what fraction does this force exceed the woman's weight? What is the magnitude of the force in the ankle joint? So we have several questions here. We have this one, what is the magnitude of the tension force in the tendon? And then this one, by what fraction does this force exceed the woman's weight? And then this one, by what magnitude of the force, what is the magnitude of the force in the ankle joint? So, several things that we can do. So first of all, the force of the floor.
It's going to be equal to the force of the weight of the woman.
Yes. Force of the floor is equal to the weight. So that is her mass, 61 kilograms, times the 9.8 meters per second squared. And when we do that math, it's going to be right around 600 newtons. What is it?
597.8.
597.8 newtons. Okay. Significant figures would put us at 600 actually. Okay, now, what is the magnitude of the tension force in the tendon?
So then we're gonna have to use the length, right? L.
Okay, so the tension force in the tendon, we're going to have to do like some of the torques situation here, right?
So then you got torque.
Can I call F tendon so I don't have to write so much T?
Yeah.
Tension, because your tendon is exerting a tension force.
And it's a tendon, so let's just call it T.
Okay.
That makes a lot of sense, right? Okay, so let's do a sum of the torques. So sum of the torques is what?
You're gonna have the torque of her toe down on the floor, right? So from the pivot point. So 597.8 times whatever 0.5 minus or 0.15 meters.
All right, so where's our pivot?
I think we should put it at the ankle.
At the ankle. I like it. It's a not well-defined area, but everything else around that is. So we can go 0.15.
Wouldn't it be less than that? Because it's from the pivot towards the end of her toe, and the whole thing is 0.15. So it would be 0.1.
Oh, okay, so that's a good question. We can go R perpendicular times the force, or we can go F perpendicular times the radius, right? Either way, we have to go with a perpendicular force times the radius, okay? So if we take this distance right here, the 0.15, let me change colors real quick. The 0.15 is the length from the ankle over, and then I'm making this line right here. So the distance over to the force, and then the force is perpendicular. So if I take this distance and my force is perpendicular, okay? So it is 0.15, and then I'm dealing with a perpendicular force. Does that make sense?
Yeah.
Okay. So it is 0.15, and then the force of the floor, which we just calculated, the 597.8. Of course, I could have written the 600 and then used the 597.8 in my calculator. Newtons. Okay, now which way is this trying to turn me?
Positive.
Is it?
No.
Yeah.
It's going negative.
Nuh-uh. This force right here is trying to get me to go that way.
But you're
That's clockwise. So I'm going to have to put a negative sign in front of that. Okay. And then the tension in the tendon, T, is what we're looking for, right? That's the thing we don't know. So which way is this one trying to turn me?
positive.
That's positive. So I'm going to put a plus sign. And then I have the distance, 0.05 meters times T. Okay. And then the sum of the torques is
Equals 0.
0. Okay, the only thing I don't know here is tension, and I know everything else. So I can solve for tension. I can move this whole first term group here to the other side, and that will actually turn it positive. And then I can divide by the 0.05 meters. So T equals positive 0.15 meters times, I hate writing all these numbers, over 0.05 meters. What do we get?
1793.4.
1793.4. Significant figures would put that at 1800 newtons. Okay, now that was the magnitude of the tension force in the tendon. That's an answer. That's the first one. By what fraction does this force exceed the woman's weight?
So then divide that by, or no.
You can divide the two.
Yeah.
We know 1800 newtons. We know 600 newtons. Divide the two. We can do that in our head. That is 3 times her normal weight. Okay. And then the third question, what is the magnitude of the force in the ankle joint? How do we do that?
That's a pivot, right?
Ankle joint's the pivot. That's right.
So,
We're talking about forces now. We know 2 of them.
Some of the forces in the what?
Some of the forces in the y direction. That's right. Some of the forces in the y direction. What do we have?
well, you got
The force of the floor, so minus force. So force of the tendon minus
you have
force
weight
of the
down.
floor.
So negative weight.
And so actually we have force of the floor, which is the weight, right? And that was up.
Which is the normal force, right?
It's basically the normal force, right? And then we also have minus the force of the joint is how they labeled it, so we'll call it that. Because that was down. And then we have plus, I called it T. And what is this?
0.
Equals 0.
Well, wouldn't the joint be just the weight?
No,
So
it's
then
not.
The force of the floor plus T is equal to the force of the joint.
Yep, if I just add the force of the joint to both sides, then I'd have the force of the floor plus T equals the force of the joint.
Which is going to turn out to be
So that's 600 plus 1800,
24.
which is 2400 newtons. Now her actual body weight is only 600 newtons. The force in the ankle joint is 2400 newtons. That's 4 times her weight.
That's crazy.
Yeah. And that's because she's doing what?
She's
Tippy toe.
She's up on her toes at a 25-degree angle with the floor. 25-degree angle with the floor. What is she doing?
stretching.
Is she stretching?
She's ballerining.
Is she a ballerina?
No.
She's trying to balance.
Really?
She's trying to reach the top shelf.
Top shelf?
She's running.
Running. She's just standing there.
So if you were running, it'd be even more force, wouldn't it?
The
Yeah.
force in her ankle.
What is she doing there? What's she doing?
Maybe she's trying to reach something.
Wait,
Or
how
she
many
wearing high
newtons are
heels?
in a pound?
No, because then we would have a force of the heel because the heel.
Right. Yeah, it's not high heels. She's up trying to reach something in the cupboard or whatever. But it doesn't even have to be a she. This could be anybody, right?
So-
Could be anybody.
So the longer your toes are, the bigger your feet are, the more force you have on the pivot point.
That's a good point because we're talking about this distance right here generating more force right here, right? Because this is creating a torque here, which is creating a bigger force here. The force here is not as bad as
So
the
if
force
you have
here.
a peg leg for a foot,
Oh, look at that. We are talking about weightlifting.
All right, weightlifting. When you're holding the body in a static equilibrium requires large muscle forces. Consider strict curling a barbell. So that means you're not moving any other muscle but the muscle that you're supposed to move,
Biceps.
which is your biceps. Everybody, when they are curling, always wandering all over the place, using their back, throwing, all this momentum into things. That's not it. You're supposed to just
Yeah.
move your biceps. So moving only the forearms. So only the lower arm, the forearms, is what's moving, which means you're only moving your biceps, or you're only contracting your biceps. So you're only moving at the elbow, and the physical characteristics as shown. So this is stationary. The rest of your body is stationary, and only this is going back and forth. Okay. A typical tendon cross-section area is 1.3 times 10 to the negative fourth meters squared. What percentage of the maximum tension the tension can support is required to perform a 110 kilogram strict curl, which is a near record lift. 110 kilograms
That's a
strict
lot.
curl. Quite a bit, right?
It's like
So the
200
question
pounds.
is, what percentage of the maximum tension can your tendon that is sitting right here hold?
So that depend on the length of your arm, wouldn't it?
I don't know. Let's see. So here, let me get rid of that circle. Okay, so let's look at what we have. What's going on here? So we have the bone that the biceps connects to right here, right? The biceps comes down and connects with its tendon right here, and we have this distance from the end of the bone to where the tendon connects, and that is 4 centimeters. Okay. So you can feel that when you're curling, or if you just like take your elbow or take your forearm up and kind of like flex a little bit, you can feel that tendon
That tendon?
coming down and connecting to your forearm. That is 4 centimeters away from the end of your bone. So we have modeled that here on the right-hand side. We have the forearm here, and then the tendon coming down with a straight up force from the end of the forearm, and that is supposed to be 4 centimeters away right here. Okay, we have the force of the joint coming down from the humerus bone here, and then we have our
That's so funny.
ulna right here. Okay, is it the ulna or is it the radius?
No, the radius is the one that moves around. The ulna is connected to the humerus.
Is it?
Yes.
Okay. So then we have the force of the barbell down here at the end where the hand is holding on to it. Okay. Now, what do we do?
I think
Well, we
need
put the
to assemble
pivot on the
torques.
far left.
Pivot over here.
I think the pivot should be the actual pivot.
The pivot is the pivot. Okay. So now what?
Do some of the torques.
Some of the. Are there any conversions we need to do?
Centimeters to meters.
Oh, we gotta change kilograms to newtons. That's it. Where do we have centimeters though? I guess we got
35 centimeters and 4 centimeters right there.
So 0.35 centimeters and 0.04.
Okay. Okay. So this guy, the centimeters, this distance here would be 0.04 meters. Okay. And then what else were you talking about?
The 35 goes to 0.35 meters. 35 centimeters.
Okay. 0.35 meters. And then we're talking about a tendon here, right? So we can probably pick up a Young's modulus for a tendon. And we're also talking about the cross-section area of our tendon.
Which is already calculated for us.
And we can probably pick up some information off of that as well. So let's pause and get some information. We need a Young's modulus and a cross-section area there. We can figure out something for that too. All right, so we have tensile strength is 100 times 10 to the 6th newtons per meter squared for a tendon, and the Young's modulus is 0.15 times 10 to the 10th newtons per meter squared for what we're talking about. So now we have F equals Y, Young's modulus, times the cross-section area over L times delta L. We can write it like this. It's fine. So we know that the tensile strength is F over A, right? So I can rewrite this equation. We know that F over A is this 100 times 10 to the 6th newtons per meter squared. Okay.
Well, we also know the area, right? The cross-sectional area.
We do know the cross-section area.
We can calculate force.
So, and I have a formula for calculating if I multiply both sides by A, tensile strength times A equals F. So that's a formula that we can work with as well. Let's now set up a sum of the torques. So based on what we see here, we have our pivot at the pivot.
Yes.
So you're gonna have,
You have
it's gonna be positive, right? Because the force is going down.
the 110 kg strip curl times 9.8 times 0.35.
Okay.
And that's all negative because it's operating in the negative direction.
Yes, this guy is trying to get me to go clockwise. So this one's negative. And then the weight of the barbell would be 100 kilograms.
That's 1078 newtons.
Oops, 110 kilograms. Oh, you calculated it?
Yeah, it's
Okay,
1078.
I'm going to write the 9.8 as well. We know it's 1078 newtons.
Yeah.
Oops, meters per second squared.
And that is all in torque, which is newtons meters. And then we have plus.
Plus, this guy is trying to get us to go counterclockwise.
Oh my gosh, that's a lot. Because you have 0.5.
Is it 0.5? It's 0.4. 0.04, right?
0.04, yeah.
That's
And then
meters.
And then N, or whatever we want to T.
Times force of the tendon.
T. Should it just be T?
No, because tension was what we're looking for. So
We can call it whatever we want. The force of the tendon. We can call it T. I'll just call this T. Force of the tendon. Okay. And what is the sum of the torques?
it's gonna be
0.
0. All right. So now we have this whole thing over here. This is negative. If I add it to the other side, it'll be positive. Divide by 0.04. We'll solve for T. So we have T equals, it's positive now. You said that this whole group here, this was 1078 newtons. So we have 1078 newtons times the 0.35 meters. Divide by 0.04 meters.
9432.5.
9432
0.5 is what I got.
is the total.
Yeah. Is that not what you got?
No,
0.35 times 1078 divided by 0.04.
0.04.
Mhm.
So it is 9432.5, but the problem is this is a barbell and we're looking for the tension in one tendon. We calculated it for both.
So divide by 2.
So we got to divide it by 2.
How do you know?
Because it said, did it say that?
Forearms. We want one forearm. So we got to divide by 2.
That'd be a lot of weight, you know.
Yeah. So what did you get? 9,400 basically.
Yeah.
Oh,
So
he's doing this?
476.
Yeah. It's a
I thought it was
double barbell. It's not a single. It's double. Both forearms are pulling this thing. So 9,400, and we're going to divide this by 2 so that we get the tension in 1. So we have an answer of 4,700 newtons for 1. Okay. Now that we know that,
Lift, right?
Okay, so the cross sectional area is going to be half, or not the cross sectional, the force is going to be half too, isn't it? So we can find the percentage.
the max tension would be, so it says what percentage of the maximum tension. So now we can calculate the maximum tension using this, the other formula. So we have the 1.3, which is the cross-section area. We have the tensile strength. So we can calculate, if I multiply both sides by the area, we have the maximum tension. This would be F max here, or T max, you could say, equals 100 times 10 to the 6th newtons per meter squared times the cross-section area, 1.3 times 10 to the negative 4th meters squared. That is a 1.3.
13,000.
13,000 newtons. Okay, So you can actually apply 13,000 newtons to your biceps tendon, and the near record lift is only using 4,700 newtons.
Jeez.
So you're saying you can put that much newtons on it before it breaks?
Yeah.
I don't know. That seems impossible.
Well, your muscle can't do it, but your tendon can.
Yeah, but what happens with it? Doesn't it happen with like that tendon can snap and your bicep like just?
Yeah,
Shoots
But
right
you
up.
don't. You're not exceeding that limit. So how does that work?
right. The tendon can handle it. Your muscle can't pull it, and possibly at the connection where the bone is, it would tear first, but the tendon can handle it. So, what percentage? We got to answer the question. So the percentage would be
13,000 divided.
4,700 newtons divided by 13,000 newtons, and then times 100. What do you got?
Why would you multiply by 100?
To move the
To get a
decimal 2
percentage.
spots.
Oh, it's because I did that backwards. No. 47 divided by 1,300 times 100. I got 362.78. Isn't it the other way around?
No.
No,
I got 36%.
36%. That's about right. So you're at 36% of the capacity.
Multiplied 470. That's why. 36.
I could probably lift that much weight.
Yeah, you think so?
Yeah.
Okay.
All right, tough guy.
All right, the masseter muscle provides most of the force for you to close your jaw. It isn't a very big muscle, but its placement generates a large force in the neighborhood of 1,200 newtons at the molars. So we have our pivot right here, and then the masseter muscle is this guy right here. You can feel it if you clench your jaw. So the force vector shows the approximate line of force of the masseter muscle, about 5 centimeters from the pivot. So it's generating this force. That's our radius right there. So compared to 7 centimeters for the molars. So the molars are back here, so we have a bigger distance there. That means at full force of the molars, you're nearly full force of the muscle. So humans don't have that big of a difference in distance there, so we're not getting a whole lot of mechanical advantage of the masseter. The trade-off, though, is the placement of this muscle's limited range of the motion of the jaw and a limited bite speed. Now, the dog jaw, though, has the same arrangement of the masseter, but the canine teeth are much farther away. So we have the same distance for the dog, but look at the distance there. So they're getting a huge mechanical advantage in this case. The dog is capable of rapid slashing bites because of the arrangement of the muscle to the teeth. Cats have a much shorter jaw than dogs. Their mouth ends around right here. What does this imply about their bite speed and force?
It's lower.
Slower and less forceful. So it's more like us. They cannot slash and tear and things like that. So if you're in the wild and you see like a dead animal, you analyze those bite marks and you can decide, was this a dog or a cat? Like a mountain lion versus a wolf, you can decide pretty easily how the bite marks were taken. Were they more puncture and like cookie cutter, or were they more slash? That kind of gives you a clue. Okay,
So
yeah,
that's
very
why
interesting
hippos have got
arrangement of the muscle there.
Such a great bite force.
Crocodiles.
Yeah, crocodiles and hippos. Look at the way that their
Oh my
mouths are
gosh,
arranged.
hippos. Yeah.
All right, in the picture, 2 people are using lift straps to carry a heavy appliance. How do the straps make moving this heavy object easier? What are they doing?
They're making the radius of the torque.
They're increasing the radius
Where are they putting those straps?
on the bottom, right? On
But
their
they're not.
forearms.
Yeah, right in the middle almost.
Notice how they're not carrying them. They're not carrying them with their hands.
So they're decreasing the radius towards the tendon.
They put
making that
the
force easier.
straps there, and they took away the torque, and so they made the force much easier to the burden much less by taking away the torque
Oh
here.
yeah, because like if you have this, there's this radius
Yep.
and it's pulling down.
That's right. You ever carry those plastic grocery bags? You know, you go over to Ron's or whatever. You carry those plastic grocery bags, put them at your elbow, and try to carry them that way. You'll have a much easier time. Bring the milk carton in towards your body as you try to carry it, and you will be able to carry it for a much longer
So you're
time.
telling me next time I need to move a fridge,